Okay. So, hello everyone. We're very happy to have Irene Valenzuela today from Harvard. She's going to talk about a CFT-Distance Conjecture. So, please, Irene.
Okay, thank you for the introduction and thank you for the invitation to give a seminar here. So yeah, my plan is to talk about the CFT-Distance Conjecture, which is based on this work with Eric Perlmutter, Leonardo Rastelli, and Komron Baffa. So please, like before I start, let me remark that if you have any question, I'm very happy if you interrupt me at any point. So the more questions, the better. Okay, so the past few years, there has been a lot of activity on the Swampland program, which aims to constrain the space of effective field theories that are weakly coupled to gravity and admit some UV completion, no, in quantum gravity. So the message is that not every EFT constructed following the rules of quantum field theory at a given energy scale can actually be UV completed in quantum gravity. There are additional constraints that you need to satisfy to allow for this quantum gravity completion. And we try to understand what these constraints are. So what distinguishes the space of UV completed EFTs that we call the landscape from the Swampland. Now, in parallel, there is a program which I think is very similar in spirit, which is the conformal bootstrap program that aims to constrain the space of conformal field theories. So it's also via the ADS-CFT correspondence, you are also trying to constrain what is the space of quantum gravity theories, right? But that have an ADS background. Now, the techniques are very different, but the goals, the motivation, and so on is the same. I think it's very similar. So you would expect that there might be some interaction between the two programs in the sense that results that we can get in one corner maybe are useful for the other and vice versa. And my talk today is going to be an example of this, in which, well, it's the result of some collaboration of people that were interested in the Swampland and people that are interested in the conformal bootstrap. And what we do is to formulate, well, some conjecture. We study the relation between some conformal operators and the geometry of the conformal manifold that is inspired actually by one of the Swampland conjectures. So let me first probably give you a bit of information about what is the Swampland conjecture that inspired the work that we have done in the space of conformal field theories. Okay, so this is a map of the most important conjectures, Swampland conjecture that we have now. So of course, try to understand what are the quantum gravity constraints that remain at low energies is a complicated task. I mean, of course, it's an ambitious program. So what we have so far are proposals. So that's why they are called conjectures. And the goal is try to understand them, prove them or disprove them, and reduce them to a minimal set of principles that we think need to be satisfied. So the conjecture that inspired the work I'm going to present you is this distance conjecture that plays a central role in this map. Now, I'm not going to talk about the others for lack of time, but I wanted to show you the map at least so I can show you all the connections that are appearing among the conjectures, because I think this is one of the most important developments in the Swampland program in the past year. So as you can see, even if it can seem a bit of chaotic, what are the conjectures that we have, actually the number of independent statements is getting reduced with the years. So this is changing quite fast. And also, if you have any question about any of the others, you can also take advantage and ask something now. Okay.
Yeah, sorry. I have a question already about this.
Go ahead.
Oh, sorry, Christian, maybe you want to ask a question?
No, go ahead.
Sorry, no, my question is really naive. It's just these dots that you draw, do they go in both directions?
No,
like
so it depends. It depends which one. So here I was very schematic. Depending on the line, some of them go in both directions. For example, I have a work very recently in which we have proven that there is a one-to-one correspondence between no global symmetries and the completeness hypothesis if one allows for a generalized notion of global symmetries, including non-invertible symmetries and so on. And then that goes in both directions. In other cases, it's more like if you take one conjecture and go to a specific type of setup of some corner, then that conjecture gives rise to a new observation, and that's the new conjecture, but it doesn't work both ways then, because it's about a constraining setup.
Okay.
Like for example, here with the fluxes, I mean, here you need to have fluxes for this to work, so it doesn't go both ways. So it depends which one. Yeah, it's something we have to continue studying.
I had the same question, so fine.
Okay, good.
Okay.
Good. I mean, the goal is try to sharpen the relations to make them really like one follow from the other and to reduce them. But yeah, in some cases it's work in progress. In some other cases it has been done. Okay, so then I'm going to focus on this distance conjecture, which is basically the statement that effective field theories can only be valid for a finite variation of the scalar fields. So that if you try to move very far away in the moduli space, like to generate some parametrically large field variation and go to the boundaries, then there is an infinite tower of states that become exponentially light at every infinite field distance limit. Okay, so that's, as I said, if we move in some moduli space parameterized, right, by this scalar manifold given by the kinetic term of our scalar fields, and we have some metric given by a field metric, then we can start at some point Q and we move near some boundary of the moduli space, so like an infinite distance limit. And then here, the theory here at P should contain an infinite tower of states that decay exponentially in terms of the geodesic distance between the 2 points. And this is something that if you work in string theory is quite natural, right? Because every time we go to these boundaries, we are used to have infinite tower of states that become light. And what they are telling you is that there is a new weakly coupled description of the theory, and it's what is behind all the dualities that we observe in string theory. So the typical example, of course, is a Kaluza-Klein compactification, that if you go to very large radius, you get the KK tower, but also if you go to small radius, you get the winding modes, and they are correlated by duality. And the power of this conjecture is that it's not only about the compactification, but in any limit in the moduli space, like when you have more complicated moduli spaces in lower dimensions, any limit, any scalar direction that you can take should involve this infinite tower of states. So from an effective field theory perspective, it's interesting because it signals the breakdown of the EFT. So we cannot have a weakly coupled Einstein gravity theory with an infinite number of states. So there is no way that the EFT is going to be valid. So when the tower is becoming light, also the cutoff is decaying exponentially. And this implies an upper bound on the scalar field range that can be described by a given effective field theory, okay, which can have phenomenological implications. I like to remark that it's not a sharp bound in the sense that it's a relation between the cutoff in field space and the cutoff in energies. Okay, so the higher the energy of the process you want to describe, the smaller the field range you can accommodate. And the precise value depends on this alpha and this exponential rate. Okay, so how fast the tower is getting light. So this is one of the most important questions of this conjecture, because this factor is supposed to be another one parameter, but we would like to do better and determine this from EFT data. So in this sense, there has been a lot of progress in the past few years by checking the conjecture in string theory compactifications to flat space. So is there any question? You can ask at any point if there is any question. Okay, so if we have more than 8 supercharges, was already proven by Ceccotti that the distance conjecture is satisfied, and there is just one type of infinite distance limit. And in the past few years, we have studied a lot the case of 8 supercharges. So for example, all the 4D n equals 2 theories that arise from type 2b, type 2a on Calavia 3/4, or 5D, 6D n equals 1 coming from F theory on the Calavia 3/4, and so on. And here it was very interesting because it was really non-trivial that the conjecture was satisfied, because you need to have very specific approach, well, behavior and counting of the BP states. And this has actually been useful also to understand better the asymptotic geometry of the Calavia manifolds. So in these works, we can give a bound for alpha, like we can, I mean, once we go to string theory, we can compute these things and identify the tower, and we have specific values for this alpha of what can be for any Calavia compactification. So I didn't put it here, but it's indeed some order 1 parameter. And also more recently, we are studying what happens in the case of 4 supercharges, in which we can even have a scalar potential. Okay, any question about this?
Yeah, so there is no general formula, no, for this alpha in terms of the data of your theory. You compute everything and then you find you fit what is alpha somehow, no?
So far, what we know from the Calavia compactifications is that this alpha is related. I mean, of course, it's related to what is the power of the scalar in the Keller potential, right? Like this is the power that we are talking about. And the point is that we have shown that in the case of BP states becoming light, no, in 4D n equals 2 and any of these Calavia compactifications, this alpha is related to the nilpotency order of some monodromy. So there is a discrete monodromy characterizing all these infinite distance singularities, which is a discrete symmetry that is the axionic symmetry in the effective field theory. And the properties of that symmetry is what gives you this alpha. So we have a formula of how it relates to this symmetry. I don't know if it's going to be valid beyond Calavia compactifications, because I have not computed that. But at least here it has some physical meaning, like it's associated to some discrete symmetry at the infinite distance singularity. So I think that's quite promising.
Okay, thanks.
Also, this discrete symmetry is of infinite order, and that's what is populating the infinite tower of states becoming light. So, yeah. Okay, any other question? Okay, so yeah, so all this, I mean, I think it's very nice and it helped a lot to understand better the distance conjecture. But everything is in flat space. So what I wanted to do in this talk is to understand what happens in ADS, in which we will also be able to give a complete general formula for alpha for any ADS background. Okay, so the question was how the distance conjecture gets manifest in conformal field theory. So this bulk moduli space gets mapped to the conformal manifolds, which is the space of exactly marginal coupling. And if there is some tower of light states, this would be translated to some tower of operators, but our goal was to try to understand exactly what is the tower of operators that arise and what light means, no? Like what's going on with them. So the setup I'm going to consider is local and unitary conformal field theories with exactly marginal couplings in dimension bigger than 2. And in a couple of slides, it will be clear why I focus on dimension bigger than 2. Okay, so I need to give you 2 pieces of information. One is that we will use the Zamolodchikov metric to measure the distances, the conformal manifold. Okay, so also like in the conformal manifold, there is also a natural notion of a metric, which is this 2-point function correlator, which will play an essential role for us. And also something very important is this work and follow-ups in which they show that free CFT always has a higher spin symmetry, and vice versa, that whenever you have a higher spin symmetry, the CFT is free. And with higher spin symmetry, I mean that there is an infinite tower of higher spin currents of spin, of unbounded spin, so spin bigger than 2, which is saturating the unitarity bound. Okay, so this is the unitarity bound. Okay, any question?
So sorry, yeah. It's important that you choose the Zamolodchikov metric for the distances. So can you, I mean, it's a bit of a choice, no? What metric you put on the conformal.
Yeah, the thing is that this Zamolodchikov metric reduces to the field metric, right, in the bulk moduli space. So it's the same. I mean, when we have a correspondence like a weakly coupled ADS dual, it's the same metric that we were using for the distance conjecture. And it happened that in terms of this metric, right, like then the towers become exponentially light, like in terms of the canonically normalized field, right? In the bulk, it has a meaning because it's like going to the canonically normalized scalar in Einstein frame. So if you measure that distance, then the states become exponentially light in Planck units.
Okay.
And it seems that, yeah, in the CFT, it also plays this role. We will also see that anomalous dimension decay exponentially, even if there is no ADS, weakly coupled ADS dual. So the Zamolodchikov metric is playing the same role.
Okay, thanks.
Any other question? Okay, so let me give you what is the conjecture that we observe, and then I will explain in detail what is the evidence that we have for it, okay, to what extent it's proven or not. Okay, so we call it the CFT-Distance Conjecture because it's going to be the analogous of this distance conjecture, but in conformal field theories. And it has 3 parts. So the first part is that all higher spin points, when we have this higher spin symmetry, are at infinite distance by measure with the Zamolodchikov metric. The second part is that all CFTs at infinite distance are higher spin points, so that the opposite is true, right? So that the only way to go to infinite distance is to have this higher spin symmetry. And we can quantify this a bit more precisely by defining the diameter of this moduli space and the anomalous dimension of the tower of operators, so how much we deviate from the unitarity bound. And then the point is that if these anomalous dimensions are always non-vanishing, then the diameter should be finite. So this conformal manifold should be compact. I'm writing here gamma 4 because Malacen and Sivoedov show that already if you have the spin 4, you are going to have all the currents of unbounded spin. So it's enough to focus on this one. And then the third part is that this anomalous dimension decays exponentially on the distance. So you can see here the analogy with the distance conjecture on the Swampland program. So more specifically, if this anomalous dimension vanishes at some point, then the diameter of this conformal manifold should diverge logarithmically. Okay. Well, in terms of this anomalous dimension. Okay, any question about the formulation of the conjecture itself?
Yes, I have a question. Like in the previous one, I mean, we didn't see like higher spin gauge fields appearing. Like here we are talking about higher spin currents becoming conserved. So it seems like on the gravity side, this should correspond to having higher spin gauge fields.
Yeah, it corresponds to have, for example, a tensionless string. Like some extended object that is becoming tensionless, not just a tower of particles, but you have some extended object, and then you have like the tower of string modes that becomes light.
But this is what happens in the usual.
So in the usual, yeah, I will we will discuss a bit more this at the end of the talk, but let me already say, so in the Swampland program, when we study this in the flat space and so on, we observe like basically two types of limits. Some of them are more related to the compactification in some dual frame. So it's really like having some tower of particles, and then they can be interpreted as KK modes and so on. And the other type of limit is also, like we have some string that is becoming light. Like, for example, when you send the string coupling to 0, that's the usual example, but also in lower dimensions, you can get weakly coupled string limits in which you get a string that becomes light. Okay. And then you will get like higher spin fields, right?
Okay.
So yeah, what we here, this is stronger in the sense that we only observe these higher spin fields. So I will give you evidence why we think only this type of limit can occur in the conformal manifold. And then we will compare at the end of the talk back with the type of limits that we get in flat space and try to understand why this difference, no? Why we only get one.
Okay, thank you.
Yeah, thanks for the question. Okay, so let me give you one example, because sometimes, at least for me, I think it's easier to have one example in mind. So the most typical example is the weak coupling limit in for n equals 2. So we take the Young-Mills coupling, some gauge field sector to 0. And we are in n equals 2, so the gauge coupling is part of this holomorphic coupling. And what happens in this cusp point, right, is that there is a free CFT coming from the gauge sector that is getting decoupled, times some possibly interacting CFT. Now, since the gauge coupling is small, we know that the marginal operator to live in order is just going to be the trace of F squared. And then by perturbation theory, we can just compute the 2-point correlation function of this and get the usual hyperbolic form for the metric as the gauge coupling goes to 0. So we can compute exactly what is this numerical factor just by taking the 2-point correlation function, and it's 24 the dimension of the gauge group that gets free. And then the anomalous dimension of the tower of higher spin operators. I mean, indeed, this is a free point, so we are going to get the higher spin symmetry. And this anomalous dimension has to be non-zero at perturbative level. So one can show that it's proportional to the gauge coupling square. And using this hyperbolic form of the metric, this is going to behave exponentially in terms of the distance, which diverges, right, as the imaginary part of tau goes to infinity. No? Because if I take the integral of this, it's 1 over the imaginary part of tau, so I get the log of the imaginary part of tau. So that's one example of the type of behavior we are discussing. Okay, any question?
So here alpha is 1 over beta, no? The alpha
exactly.
Before.
Yeah.
So okay, at large n it becomes super small. This is I go.
Yeah, here we are going to. I mean, we are moving in a conformal manifold, so we are keeping the central charge fixed, which means that we are also keeping n fixed.
Okay.
So we are not taking the limit of both gauge coupling to 0 and n going to infinity, but keeping n fixed to some value and going to the limit in which the gauge coupling goes to 0.
I see. Otherwise, you okay? Yeah.
Otherwise, it's like decompactifying as well, actually, from the bulk perspective. So it's a combined limit. But yeah, like if n is large, then you have a weakly coupled ADS dual, and you have this beta just in terms of the dimension of the gauge group, which is given the alpha.
Okay.
I will show you later. Okay, so I'm showing you this example not just because it's a useful example to keep in mind, but because actually all known examples of infinite distance limits in conformal manifolds are of this type. So in all known examples, the marginal coupling is going to correspond to some holomorphic gauge coupling. And we are actually going to propose that this is really the only way in which we can go to infinite distance limit, to an infinite distance limit by sending some gauge coupling to 0. So let me make a comment about d equals 2. So why we restrict to dimension bigger than 2 is because, well, obviously the conjecture by itself, the way it's formulated doesn't hold in 2 dimensions because CFTs, 2-dimensional local CFTs always have higher spin currents. And whenever you have higher spin currents, doesn't mean that the CFT has to be free. Okay, so the story is different. However, there is an analogous conjecture already in 2 dimensions, which also says that at infinite distance, you should get some tower of operators that saturates the unitality bound, but it's about scalar operators instead of higher spin. So in that case, this author conjecture that indeed the only way to go to infinite distance is to have the scalar gap going to 0, the anomalous dimension going to 0. So it's very similar, and actually if we combine both conjectures, then in any dimension we always get an infinite tower of operators whose anomalous dimension vanishes at infinite distance, and this is what would be analogous to the distance conjecture in the Swampland program. But it seems that in 2 dimensions it's about scalars, while in higher dimensions we always get higher spin fields. So let's try to understand this a bit better. Okay, so what is the evidence that we have from conformal field theories for this conjecture? So first of all, I'm going to focus on superconformal field theories because it's the only known example in which we have a conformal manifold. Okay, when we have superconformal field theories with at least 8 supercharges. So by superconformal representation theory, we can one can classify the possible theories in which that allow for some conformal, for some marginal coupling. And we can have either 4-dimensional superconformal field theories with n equals 1, 2, or 4 marginal couplings, or 3-dimensional superconformal field theories with n equals 1 and 2. Now, the case of n equals 1 is a bit strange, and actually there are no known examples of conformal manifolds that preserve n equals 1. It's something similar to why we don't have conformal manifolds without supersymmetry. The thing is that here the marginal coupling is in the top component, right, of a long multiplet, so one would expect that stops being marginal at next order in conformal perturbation theory. But I don't know, it would be of course interesting if one can find some examples. So for this talk, I'm just going to focus on the cases in which we know examples. And notice that I'm not focusing on higher dimensions because in higher dimensions, these superconformal field theories are always isolated points. So I cannot move in the conformal manifold. Okay, any question? Okay, then let's go for it. So what is the evidence that we have for the first part of the conjecture, that all higher spin points are at infinite distance? Well, this is proven if we can prove that all higher spin points must contain free vectors, because then by the perturbative argument that I show you, we can compute the 2-point correlation function and the metric, and we get this hyperbolic form, so it's going to be at infinite distance. So the whole point is whether we have free gauge fields or not. Now in 14 equals 2, the thing is that there is no candidate operator within the hypermultiplets with the right quantum numbers of the chiral primary to construct a marginal operator. So indeed, there is the only way is that the higher spin points contain free vectors, and therefore they are at infinite distance. In n equals 1, for the n equals 1, again, it must contain free vectors for a different reason. It's just that the conformal manifold is given by we have to quotient over the global symmetry group. So the marginal operators must be singlets, right? And the problem is that there is no way to cancel a U1 charge, which is given by rotating all the faces of the the chiral multiplets simultaneously. So there is no way to cancel this U1 charge for a marginal operator constructed only from the chiral sector. So we need to construct the marginal operator using the vector multiplets. And therefore, again, it's going to contain 3 vectors and it's going to be at infinite distance. So in 4D superconformal field theories, this conjecture is proven. And I'm just saying here in superconformal field theories, I will tell you later why in 3D there is no problem. So, okay, so this part of the conjecture is easy. Superconformal field theories is proven. But the second part of the conjecture is less trivial. So this is the part which is non-trivial from our proposal, which is that all CFTs at infinite distance are higher spin points. So that the only way to go to infinite distance is to have these 3 theories, right? Okay, so this is true if the only way, we think is related to the fact that that conformal perturbation theory is breaking down at the higher spin points. So the difference, let me explain. So for example, in 4D n equals 2, it's going to follow from this decomposability conjecture, in which it was proposed that any n equals 2 superconformal field theory can be constructed from gauging a subgroup of the global symmetry group of a collection of isolated superconformal field theories. Now, if this is true, then our statement also follows, because then the only way, right, to go to infinite distance is to ungate one of these gaugings, to send the gauge coupling to 0. And there is no other type of marginal coupling that we can play with. In 4D n equals 1 is less obvious, because in addition to these gauge couplings, we also have matter superpotential deformations, right? So you could ask why these superpotential deformations cannot give you new infinite distance points, why everything is about sending a gauge coupling to 0. And here is where I wanted to discuss of the conformal perturbation theory breaking down, because there is a fundamental difference, I think, between these 2 types of marginal couplings, which is that when we send a gauge coupling to 0, conformal perturbation theory is breaking down, right? And I think this is related to the fact that we are engineering some infinite distance in this conformal manifold, so that the 2 points are at infinite distance. While for a superpotential deformation, we can send the superpotential coupling to 0, or it can be as small as we wish, and conformal perturbation theory is not going to break down. So this seems to be more associated to a finite distance deformation. So it's something that doesn't cost an infinite distance, and we can make the coupling as small as we wish, and nothing drastic happens. So this intuition is what gave us to formulate this proposal that all the infinite distance points are higher spin points, and also the fact that there are no counterexamples, so that all the examples we know of infinite distance points are generated by sending a gauge coupling to 0, and all the examples we know of matter superpotential deformations are at finite distance. But it has, for example, non-trivial implications for cases in which it's not known what is the metric for some superpotential coupling. Like, for example, we are saying that the conformal manifold must be compact if there is no weakly coupled description. So if we cannot send, if there is no some dual description in which we are sending some gauge coupling to 0. So this has interesting implications, for example, for the IR n equals 1 superconformal field theory that emerges as RG flowing point of n equals 4 super. So it's not known yet if this conformal manifold in the IR is compact or not, but it's not known either whether we have a weakly coupled description. So either we have a weakly coupled description, or the modulus or the conformal manifold should be compact, which contrasts with what happens in n equals 4 super. Okay, any question? Okay, then, so this is the non-trivial part. If we assume that that's true, then the third part also follows automatically, because if the marginal coupling is a gauge coupling, again, we can use our perturbative argument, and then the anomalous dimension will decay exponentially on the distance. Okay, so I argue for this in 4-dimensional theory. So you could ask what happens about 3D superconformative theories. Now, the thing is that here, the gauge coupling is not marginal anymore, right? It's a relevant coupling. So all the marginal deformation are of superpotential type. Now, according to our proposal, this means that we would expect that all 3-dimensional conformal manifolds should be compact, because we are proposing that the only way to go to infinite distance is to send a gauge coupling to 0. So this is, I mean, I think this would be something interesting to study in more detail. I put here one example in which indeed these people show that this 3-dimensional conformal manifold is compact, and it's just a nice example that I like because it's very simple and very clear and useful. So here there are three singularities in this conformal manifold, and one can study all the symmetries and right, the monometries around and so on. And the final conformal manifold that arises upon a quotient over the complexified global symmetry group is CP1 over S4, so it's a compact conformal manifold. So these singularities are at finite distance indeed. And I like it also because it matches with my work in flat space, in which we were classifying all possible singularities in the modular space of Calabi-Yau manifolds, precisely by studying the monodromies around and all these symmetries. And we know that in order to go to infinite distance, you need to have one infinite order monodromy. So in these cases, it matches that the group is just S4, and therefore it's a compact modular space or conformal manifold. Okay, any question?
Sorry, Irene.
Yep.
What is S4 here? You mean the permutation group?
Yes.
Okay.
Yeah.
Thanks.
Yeah, that's why it's compact. Okay. Okay, so if there are no more questions about this, let me then come back to ADS and tell you, what we have learned from this analysis in conformative theories in the bulk, right? So what we learned in the bulk from this. Now, I want to remark that the conjecture in principle is valid for any conformal manifold, so it doesn't matter whether you have a weakly coupled ADS dual or not. But if you have a weakly coupled ADS dual, then we can see what does it mean in the bulk and compare it with the distance conjecture on the Swampland program. Now, what we are saying is that in ADS, with dimension bigger than 3, all infinite distance points for fixed ADS radius, because we are keeping the central charge fixed, give rise to massless higher spin string excitations. So we are going to get some tower with a mass that decays exponentially. And it's important to determine the alpha that I was talking about at the beginning, this exponential rate. It's important that we write everything in Einstein frame and we measure the distance in Planck units. Okay, that's how the conjecture is formulated, always comparing with the Planck mass. So that it disappears when gravity is non-dynamical. Now, in order to, so alpha is going to be 1 over beta, as we said before, where beta was the coefficient of the Zamolodchikov metric, but we also have this conversion power because in order to write everything in Planck units, the central charge, right? We need to multiply by the central charge. So if I replace what is the value of beta that we got for these weakly coupled gauge points and write it in terms of C, then alpha is given by the square root of 2 times the central charge, so it's written in Planck units, over the dimension of the gauge group. Okay. And this is great because you can see that when written in Einstein frame, then this exponential rate is going to be lower bounded because the dimension of the gauge group cannot be bigger, right, than the central charge. So let's see what is this lower bound. So first, I want to point out that now alpha has a very concrete meaning in the sense that it's giving you information about what portion of the theory is getting free, right? Like how much is getting free. And as we said, it's lower bounded because, well, for example, we can write n equals 2, the dimension of the gauge group can be written in terms of the contribution from the vector multiples to the central charge. And since it cannot be bigger than the central charge itself, this is going to be bigger or equal than 1 over the square root of 3. In n equals 1, we can do the same exercise, and then it's going to be bigger than 1/2. So it's always some order 1 parameter. Let me also point out that we get a stronger bound. I mean, maybe I should say also that it's interesting that we get a lower bound because a lower bound is what you need to get an upper bound on the field range. Okay, so we are all the time looking for lower bounds of this exponential rate because this gives you an upper bound of what is the field range that the effective field theory can accommodate. Okay, so these are lower bounds in general, but by checking, we were also interested by checking examples, what is the minimum value that we can actually get. And by checking example, the minimum value we observed was 1 over the square root of 2, which is precisely given by n equals 4 super Yang-Mills. And this stronger bound is going to apply for any n equals 1 super conformative theory with a Sasaki-Einstein dual, because then we can compare the central charge with the central charge of n equals 4 super Yang-Mills, and the alpha, right, that is proportional to the central charge is going to be always bigger than the one corresponding to n equals 4. And we also check all possible n equals 2 and n equals 1 super conformative theories with simple gauge group that has been classified and large n limit. And in all these super conformative theories, they have different tables in the paper. Indeed, this bound is satisfied, but not only that, we only found 3 possible values for alpha. So it's more constrained than what one could naively think. You cannot get just any value of alpha, and at least with this simple gauge group, there are only 3 possible values that appear. And I have to say that at the moment, I don't have a very good explanation for the 3 values. They seem to group the different superconformal theories in a bit of a random way for me, but it would be interesting to give some meaning for this. In the same way that, for example, in the works in flat space, indeed, we also get very few values of alpha, and this was correlated to these monodromies and these symmetries. So that's why we only got very few values, and this was very useful to classify all possible singularities and what is the meaning of the physics of these singularities, like what is the resolution of the infinite distance limit, what is the properties of the tower that is becoming light. So I would like to do the same type of analysis in the future regarding these 3 values here. Okay, any question?
So essentially, okay, this means that the Zamolodchikov metric near the singularities always goes in a certain way,
Yes.
no? Because this is there's only some classes.
Yes,
okay.
indeed. Yeah, because the anomalous always behaves the same way. So it's about the Zamolodchikov metric. Yeah, and it's we have to, maybe for some of you that are more expert in conformative theories, if you check it more carefully, you realize why, but I don't have an explanation why of these 3 behaviors. Okay. I just put here a few examples, just to say, like, for example, if we get orbifolds of n equals 4 super-Yang, it's a nice example in which one can see this intuition in which the alpha is telling you what portion of the theory is getting free, because depending on how many gauge couplings we send to 0, so n, right, is the maximum number of gauge couplings that we can send to 0. So k here is going to be the number of gauge couplings that we send to 0 in that limit. So it's bounded by n. And the smaller value corresponds to the case in which everything decouples, and the larger value to the case in which only one sector decouples. The case of classes theories, I put it here because I also find it quite puzzling in the sense that the value of alpha that we get actually depends on n, because the central charge goes as n cubed, while the dimension of the gauge group goes as n squared. And this is puzzling from a bulk perspective, because it means that the tower is getting parametrically light at large n, right? When n is large. So in the weak, in the Einstein gravity limit, we get this parametrically light tower, and it's the first time in which I find one example of this sort. Like on all the flat space examples I had before, there was never this parametrically light behavior. It was always some order 1 factor, and that's it. So it's interesting. Okay, so to finish, I want to compare a bit more the results on the conformal manifolds to the distance conjecture in the Swampland program. So if there are no questions about the previous part, then let's go on with this. Okay. Okay, so first, 2 comments. So this CFT-Distance Conjecture holds regardless of whether the CFT has a semi-classical ADS description. So in that sense, it's more general than the distance conjecture in the Swampland program, which in principle was formulated only for EFTs with a weakly coupled Einstein gravity. Now, so in that sense, it's more general, but it's also more constrained, right? Because in the case in which we have an ADS background, we are saying that something stronger than the distance conjecture is realized in the sense that we are specifying the spin of the tower, right? We are saying that it's only higher spin and not any tower of states. So the other thing is that we get a universal lower bound for the exponential rate of theories with ADS background, which is nice, and it's very useful. We can compare it with other bounds. So here I wrote what is the bound that we got for Calabi-Yau manifolds. So in the case of a 4D n equals 2 for a Calabi-Yau compactification of 5D n equals 1, if that comes from M theorem Calabi-Yau threefold, the bound is given by 1 over the square root of 6. And there is also this other proposed bound for alpha based on the TCC, which is another Swampland conjecture. I just put it here because it happens to be that this lower bound is 1 over the square root of 12, which is also what one obtains here as the common denominator. So it might be just a matter of coincidence, but I think it's interesting to point out. And it's nice also, as I said, like that we get 3 different values, because also in the case of the Calabi-Yau, we also get very specific values, which are also associated to the possible behaviors of the metric near the point, which comes from an origin from this correlation to the monodromies, no, and the discrete symmetries. And it's also to correlate it to how fast the gauge couplings are going to 0, because that's related to the metric. Okay, and finally, it fits also with refinements of the distance conjecture that have appeared in the Swampland program. So we actually propose that there is always some vanish in P-form gauge coupling at every infinite distance limit. and this fits here because it seems that infinite distance limits are about weakly coupled gauge points of some p-form gauge coupling. In flat space, sometimes this can be a zero form, like an axion, and that's why we also get tower of particles and so on. Here it seems we only get higher spin, but there is always some gauge coupling that vanishes, and this is correlating the distance conjecture with the absence of global symmetries, right? Because if we have some gauge coupling that goes to zero, or we got some weakly coupled description, then it means that the tower is giving you some quantum gravity obstruction to restore that global symmetry that would appear in the limit. Okay, so it quantifies how close you can get to the situation of restoring a global symmetry. Now, it also fits, so we have this emergent string conjecture. This is what I said at the beginning, after a question, that in flat space, it seems we always observe that we get either the compactification limits or weakly coupled tensionless string limits. Okay, so a limit in which a string becomes tensionless. And these people actually propose that these are the only two possibilities. Okay? Now, here we only get the first one, right? We only get like higher spin fields. So it means that we don't get the compactification. And that's correlated then to the fact that since we are keeping fixed the central charge, right? We do not allow the ADS space to decompactify. Okay, that would be another limit. But we move on the conformal manifold, so we move along some marginal coupling. So if we don't allow the ADS space decompactify, it means that, and we only get higher spin fields, what we are saying basically is that there is no way to decompactify some extra dimension without decompactifying as well the ADS space. Okay, so it's correlated to this absence of scale separation that we observe in ADS, and that was also proposed as some general feature of quantum gravity in this ADS distance conjecture. So that's the reason why we only get higher spin fields. That's the intuition, that we cannot decompactify some extra dimension while keeping fixed the ADS radius. Any question? Okay, so of course, this is based on examples right now, and this intuition that the conformal perturbation theory should break down at infinite distance, but it would be very interesting to study all these superpotential deformations in more detail and try to relate it to this absence of scale separation. Okay, so just to finish, I also wanted to compare our results with the work that we are doing in N equals 1 for the EFTs, because by studying the distance conjecture in 4D effective field theories in the bulk, right, with N equals 1 supersymmetry with only 4 supercharges, we are also discovering that higher spin fields are playing an essential role. So in these works, I propose that actually there is, even if there is sometimes a KK tower or another tower of states that become light faster, there is always a string as well, so that you cannot get rid of the higher spin fields, even if there are also other things. And that's something that we realize by checking not just the leading tower, but all the tower of states that are becoming light in the infinite distance limits. And we show that in N equals 1 for the EFTs, we always get some tensionless string that becomes, well, some string that becomes tensionless in the infinite distance limit. And we propose that all infinite distance limits in 4D EFTs can be realized as RG flow endpoints of an axionic string. So that there is this correlation, there is this interpretation between moving in the moduli space towards an infinite distance boundary and studying the back reaction, the back reaction profile for a scalar that is induced by the presence of a string, of a higher dimensional object, in this case, a codimension 2 object. And this back reaction profile can be interpreted as some RG flow of the couplings. So there seems to be some correspondence between this RG flow of the couplings and moving in the moduli space. And this could be useful, this interpretation could be useful to something that is starting to get formulated, which is this moduli space holography, which is like trying to do holography in the moduli space, so that we think that a lot of information of the moduli space is already encoded on the boundaries in these infinite distance limits, and one can try to reconstruct the geometry like in the moduli space, deeper in the moduli space, from the information that we have in these infinite distance singularities. Okay, so this is a proposal that we are studying this year, and we check it, of course, from string theory compactifications, like type 2 on orientifolds, and also M theory on G2 manifolds, and heterotic on Calabi-Yau threefolds. But from a bottom-up perspective, one can also derive this just from assuming that there is some axion at every infinite distance limit. So if you have an axion, then you are going to have the string magnetically charged under the axion, and just the properties of the string from a bottom-up perspective give you the result that the string becomes tensionless at infinite distance. And one can rederive the distance conjecture from a bottom-up perspective if this string satisfies the weak gravity conjecture. And as I said, the only assumption in this bottom-up derivation of the distance conjecture using these higher spin fields, these strings, is that there is an axionic symmetry that is restored at large field distance, so that the Keller potential always takes this form in which one gets the log of some function that depends on non-periodic scalars, and it preserves some axionic symmetry at perturbative level. Okay, so this was just some last comments. If there are no questions about this, then let me summarize. So I have shown you this CFT-Distance Conjecture, which we propose that there is always some tower of higher spin fields whose anomalous dimension decay exponentially as at infinite distance in the conformal manifold, which is inspired by the Swampland distance conjecture, but supported by all the data that we have from superconformal field theories. And this is, as I was remarking, this is valid beyond Einstein gravity, which also makes me wonder to what extent the Swampland conjectures are actually restricted to weakly coupled gravity, or some of them might hint some more general quantum gravity principle, regardless of whether we have an Einstein gravity description. So let me thank you for your attention and ask if there is any further question.
So I had a question, if you don't mind. A bit more, maybe philosophical, I don't know. But so it seemed to me like part of the argument for this tower of higher spins in the CFT. A lot of the argument is based on the fact that you have to have some kind of weakly coupled gauge field when you go near these points, no? And that seems to follow largely from representation theory of the SCFT. I mean, how much data, like dynamical data, enters in this proof?
The part that doesn't follow from representation theory is that you cannot engineer the infinite distance with a superpotential.
I see.
Coupling in n equals 1 for T. That's the part which is less trivial, let's say. And that's the part, I mean, exactly. So all the other parts can basically be proven in superconformal field theory. The part that we are not able to prove is this part, that the only way to go to infinite distance is to have this gauge coupling, because what about the superpotential deformation? And then it's just based on the examples that we always get this, and on this intuition that we think that something drastic should happen if you have an infinite distance. So conformal perturbation theory should break down, and that doesn't happen with the superpotential deformations.
I see. Okay.
But yeah, it would be nice to have a better, like a more rigorous proof than just this intuition. But yeah, the rest, a lot of the other things are very, I don't know how to say, rooted, right, in properties of the conformative theory and representation theory. And it happens the same in the distance conjecture in the Swampland program. It's kind of, it's too natural. It's very natural to have always this tower of states. So I think there is something, I mean, that's why I think it's one of the most widely accepted conjecture. I mean, that you have this tower. It's just, it's hard to prove why you should have it from a bottom-up perspective. And what goes wrong otherwise.
Okay. So are there any more questions, comments? Okay, well, if not,